All right, in this video, I want to take a closer look at vertical motion and some of the special things we have to consider and think about when applying kinematics to vertical motion. The same four equations that we've learned with horizontal motion can be applied to objects that are moving vertically. Objects that are moving vertically are those that are in free fall and objects that are launched straight upward into the air. The motion of these objects has to be straight up or straight down for simple one-dimensional motion to be applied to them. Now, there's a few things to consider, a few things to think about when dealing with objects that are in free fall and launched directly upward. One of which is that the acceleration of these objects will be the acceleration due to gravity. And the acceleration due to gravity, or AG, is 9.81 meters per second squared on Earth. It differs from one planet to another. On Earth, 9.81 meters per second squared. This number can be positive or negative depending upon the motion of the object. In this case, the positive and negative sign doesn't mean up or down. What it instead is going to refer to here is the direction of the object's motion relative to the acceleration due to gravity itself. If the acceleration due to gravity is in the same direction as the object's motion, we can treat it as positive acceleration. It's going to speed up. If the direction of the object is opposite of that acceleration due to gravity, then we can treat it as a negative number, indicating that the object is going to slow down. So one way we can apply this is to think about the object in free fall. The object is moving downward. Acceleration due to gravity always works downward towards the Earth. The motion of the object and the direction of the acceleration are the same. This would be positive acceleration, 9.81 meters per second squared. Again, the positive sign indicating that the direction of the acceleration is the same as the motion of the object. It's the same way we treat it in horizontal motion. In horizontal motion, if we had an object that was moving to the right, and we had, say, an acceleration of 2.1 meters per second squared, also to the right, this would be a positive number. It would be positive 2.1 because both the acceleration and the object's motion were in the same direction. The object would be speeding up, which would be positive acceleration. In the case of an object launched directly upward into the air, the object's motion is upward, while the pull of gravity is downward. They're in opposite directions, so this object would slow down. The slowing down is negative acceleration. So we can use negative 9.1 meters per second squared in these cases. And again, this would be exactly the same as an object in horizontal motion. So if I have an object that's moving to the right, but my acceleration is to the left, this would cause the object to slow down, so this would be a negative acceleration. Positive sign indicates that the acceleration is in the same direction as the object's motion, causing the object to speed up. Negative signs and accelerations indicate the acceleration is in the opposite direction of motion, telling us that object is going to slow down. One way to look at it. The other way to look at it is to think about positives meaning up and negatives meaning down. Downward motion would be considered negative displacement. So your delta x in these problems could be treated as a negative number. So if it falls 10 meters, our displacement would be negative 10 meters. but a negative displacement because we're going down. And gravity, because it's also going down, would be considered a negative number as well. This would allow your negative signs to resolve each other in your calculations, giving you positive times, for example. You'd also have to treat your velocities negative in this case too. Your VFs and your VIs would have to be negative numbers. This would be negative whatever. Your VI, if you're just dropping, it would be -0. Everything would be treated negative in a free fall situation. So again, using downward as a negative number, your acceleration would be negative, your delta x would be negative, your velocities would be negative because everything's downward. And again, that would allow your signs to resolve themselves correctly in your math, giving you positive times when you do your calculations. In the upward motion, again, the gravity is going to be negative. That's always downward. But the other things end up being positive. Our delta x is positive because we're going upward, and our velocities will be positive because we're going upward. Again, it's another way of addressing it. It's another way of making sure that when you do something like calculate a time, you end up with the correct values. When you're doing your velocities, you get speeding up where it's supposed to be speeding up, slowing down where it's supposed to be slowing down. To me, this is more complicated as opposed to just thinking about direction of acceleration versus motion of object. So I prefer to do it the first way, but whatever makes more sense to you, that's always the way things should be done. The other thing I want to mention about math with free falling object does relate to time. There are oftentimes situations where we're talking about an object that is thrown up in the air and allowed to fall back down to the ground again. So we take the object, we throw it upward, it travels to its maximum height, falls back down to where it started from again. There's a couple things that you need to know about this. When this kind of situation happens, the time that it takes to go up will be equal to the time that it takes to go down. So if the ball takes 2 seconds to reach its maximum height, it will take the ball 2 seconds to get back down to its original starting position again. The time it takes for the object to go up will be the same as the time it takes the object to go down. The displacements will be the same. So if it's 3 meters upward, it's going to fall 3 meters downward. And there'll be some relationships amongst the velocity. When you throw an object upward in the air, that object will travel up, slowing down as it goes upward, till eventually for a split second it stops. And then it immediately begins to fall back down to the ground again. So no matter whether we're talking about the object going up or the object coming back down again, there's a velocity of 0 to be had in our calculations. For the upward part of it, though, that is our final velocity, it will end its upward motion at 0. For our downward part of the velocity, this would be VI, because it's going to start at 0 and speed back up. So whether you're talking about the upward portion of the object's motion or the downward portion of the object's motion, there's a 0 meter per second velocity to be found. It's VF if you're focusing on the upward portion, it's VI if you're focusing on the downward portion. There's also a relationship, very similar relationship in velocity found at the bottom. If we were to have launched this upward at 12 meters per second, that means the initial upward velocity is 12 meters per second. And it does mean that the downward velocity is also going to be 12 meters per second. But in this case, it's going to be VF. So we have the same numbers at the top and the bottom, but we label them in an opposite fashion. If we throw the ball upward at 12 meters per second, our initial velocity on the upward portion of its motion will be 12 meters per second, and it will end at 0. Then as the object is allowed to fall back down to the earth, 0 becomes its initial velocity, and it will reach the same speed at which it was launched with, ignoring air resistance. That 12 meters per second becomes the final velocity. I tell you this because we end up having to split this motion in half when we're talking about the problems that we do. The problem says something about a ball is thrown up in the air. It takes 4 seconds for it to go up in the air and come back down to its starting position again. How high did the ball go? We are focusing entirely on the upward portion of its motion to try to figure out how high the ball goes. You know the initial velocity is 12 meters per second. You know the final velocity is 0 meters per second. The only thing you have to do in a situation like that is to split the time. So it says 4 seconds to take its complete journey. 2 seconds of that is the upward component. So you would use the 12 meters per second as your initial, the 0 meters per second as your final. You'd use 2 seconds as your time to figure out what the maximum height of that object was. Acceleration being negative 9.8 meters per second squared, or you have to play around with the signs on the displacements and the accelerations to make it all work out. But again, this is another thing that comes up quite often with kinematics, dealing with vertical motion as well as horizontal motion. The last thing worth mentioning, because it's important to understand, acceleration is always 9.8 meters per second squared downward on Earth. And that is regardless of the mass of the object. So we can take a really big object and a really small object and drop them from the same height. And what we would find is that they would keep pace with one another if there is no air resistance to consider. So after 1 second of free fall, my big object would be here. My small one would be there. They'd have fallen the same distance and they would attain the same velocity. After 1 second of free fall, they'd both be moving 9.81 meters per second squared, or meters per second. They would fall the same distance and they would have reached the same speed in the absence of air resistance. After second number 2, the big object would be here, the small one would be there. They will have fallen the same distance, and they will again both have reached the same velocity. They'd both be traveling at about 19.6 meters per second. And again, if it takes 3 seconds to get to the ground, the big object and the small object would hit the ground at the same time, having traveled the exact same distance, and they would hit the ground going the exact same speed. Nowhere in any of these calculations, nowhere in any of these kinematic equations does mass come into play. So it doesn't matter what the mass of the object is. We've accelerated at 9.81 meters per second squared, meaning that they will fall the same distance, attain the same velocities, no matter what. Again, just something that I know that is taught in physical science. I'm fairly certain it's taught in middle school, but to make sure everybody is on the same page. All right, that's about it for vertical motion for now. We'll get more into, I'm sure, when we get to gravity and stuff like that.